Hello everyone. In this lecture, I'll be explaining the Möbius inversion. So the function, it's using the Mobius function, which I introduced last lecture, and also I will be explaining the Euler's function, why it's multiplicative, and so on. So I begin with the Euler's function because it's the rather smaller part. So we'd like to prove that phi mn is equal to 5n of n. This is given that m and n are coprimes, and we already know that, so 5 1 is equal to 1. So this is the main, this is the first condition of the multiplicative function, so now we just have to make sure that this is correct. In order to prove this, so there's this theorem that if there's some number r that is coprime with the product m n, then this number is coprimes with each of the r of m and n. As we can see, so if the r doesn't share any divisor with m and also doesn't share any divisor with n, then it has to not share any divisor with the product mn, also the other way around. So if we don't have any divisor here, so we basically don't share any divisor with any of those. So we have this condition. So from here we remember the residues table from we elaborated while explaining the Chinese remainder theorem. So we had this correspondence between, we have some number, let's say s mod n. This has correspondence to the pairs of s mod n and s mod n. So here, if you remember, this part was the LCM of m and n, but since they are coprimes, so just the product. So here we have this correspondence. So for all the numbers from 0 until mn minus 1, there is a 1-to-1 correspondence with all the pairs that is coming from here and here. So here the values from 0 until m minus 1, and here from 0 until n minus 1. So this is R1 and this is R2. So all these possible pairs will correspond to one number from here. So there's a 1-to-1 correspondence here. So from this, we can basically just find, if we want to find all the numbers that are coprime with m and n, we find all the numbers s that are coprimes with m and n from this list. And each of those will correspond to one pair. And this one pair has to be also, so the R1 has to be a coprime with m, and the R2 has to be coprime with n. So this, let's say, it's a function one way, and to make it in the other way. So if R1 is coprime with m and R2 is coprime with n, and the product of them, sorry, not the product, and the corresponding number here, if it's s, then if R1 is coprime with m and R2 is coprime with n, then the s is coprime with mn. So this is, let's say, the other way of the function. So the function goes both ways. There's a one-to-one correspondence if there is a pair of coprime numbers, like coprime with the corresponding column, then this will correspond to all the coprimes that in this table. So if we would like to see this example, so I'll show an example, but so I'll just finish the argument here. So here basically we have all the numbers that are coprimes within this list have this size. So these are all the numbers here. And here we get all the coprimes of M times all the coprimes of M. So basically those have the same size because there's a one-to-one correspondence between all the coprimes here times the coprimes here. So it's a Cartesian product, so all the pairs of coprimes. So this all pairs corresponds to all the coprimes here. So that's why we have this equation. So basically this proves the formula. To see an example of this correspondence, we get so this is the residual table. So the first column, which is in blue here, these are the numbers mod 30. And then this second column here are the numbers mod 6, and the third column is the numbers mod 5. Just wait like that. So we can go through the numbers that are coprimes with 30. So not 0, not 2, not 3, not 4, not 5, not 6, not 8, not 9, not 10, not 12, not 14, not 15, not 16, not 18, not 20, not 21, 22, 24, and so on. So all of these numbers share either the 3 or the 2 or the 5 as a common divisor. We eliminate all of them. And for the 6, all the numbers that are coprimes with the 6 are basically, so the 1 and the 5. All the others has to be eliminated. Here, and here all the coprimes of 5, so it's all the numbers except the 0, because 5 is a prime number. All the other, the non-zero numbers will be coprime. So as you could see, so all the pairs here shows all the possible combinations from the values here from 1 to 5, and here from 0 to 5, and here from 0 to 4. And here they all corresponded 1-to-1 to some number from the first column, which is 0 to 29. So here what we have, as we can see it, so the numbers that are coprime with 30, they will have all the pairs. So they have all the pairs here that both are coprimes with their corresponding columns. So even here, this 2 is coprime, but because the other 2 is not, so we don't take this pair. So here, this, and this, and this, and this, and this, and this, and this. So here we're left out with all the numbers that are coprime with 30. So basically we have the 5, 6 is equal to 2. and 5 is equal to 4, and phi of 30 is equal to 8, which is the product, as we saw here. So yeah, 1, 2, 3, 4, 5, 6, 7, 8. So basically this is a demonstration why the proof is true. So now we can proceed to a formula that would compute the phi. So since it's multiplicative, so it's enough that we be able to compute it for some power of some prime, and then we can generalize it for all numbers. So here we have p to the power of k, means we have, let's say, from all the numbers that are from 1 to some value x. So the numbers that will be not coprime with p to the power of k will be the numbers that are divisible by p, because p is a prime. So if there's a common divisor, it has to be this prime at least. Basically, we have to have, so it's all the numbers in this range. So it's from 1 to x, so the count is x, minus, so the numbers here that are divisible by p. Here, we have to do it like that. So these are the numbers that are coprime with p or any power of p in this range. So here, if we use this x to be equal to p to the power of k, we end up having this. This is equal to p to the power of e, and this is p to the power e minus 1. Sorry, this like that. But as we can see, so this we cannot generalize it for the, just if e is equal to 0, then it's 5, 1. So this formula will not be true anymore, but it's because here we assume that the x is greater than or equal to 1. And also we assume that from this part here, if here the x is equal to 1, then this flooring is actually equal to 0 on top, and not equal to 1 over p. So that's why this formula I can only use if e is greater than 0. So this we can generalize to how to calculate the phi in general. We can factorize a number, or this. So it's p. This is the phi of p1 for e1, and this is the phi e2. So we keep multiplying this. This is also equal to, if we use n, this one. So it's another way to compute that. Alright, so this was the phi. Then I moved to the new function, which is the Mobius function. So the mu, we defined it as the inverse of the function I in the Dirichlet product. It means that the summation of mu dot I, so the mu dot I is equal to E, which means that the summation over the divisors and d Then it's times phi of n over d, as we know that this is equal to 1, so I'll not write it. So this is equal to e of n. So there is a formula that I use for computing the inverse, but so we can plug it in here, or I'll just derive it here for how to compute the mu. So basically, if n is equal to 1, so we have that mu of 1 equal to 1. And also here we can see that the mu is multiplicative because it's the inverse of I, and which is a multiplicative function. So here we have the mu is multiplicative. So we already could know this because it's multiplicative without executing this part. So anyway, so since it's multiplicative, we can try to compute it for a power of p to the power of k. If this k is greater than 0, so it means that if we go to all the divisors of p to the power of k, of p, so this would be equal to e to the of p to the power of k, which is equal to 0, because here this number is greater than 1, and the e will be, so e of p to the power of k will be 0, because the number is greater than 1. So here we can find that we go from I equals 0 until k, p to, so we take the mu of p to the power of I. This has to be equal to 0. So basically, if we execute this, so we don't put k equals 0, so start from k equal 1. It means that mu 1 plus mu of p equal to 0. So mu of p is equal to 1, to negative 1 for any prime. And then we'll find out that, so this if we put k is equal to 1. And then if we put k is equal to 2, then we have this summation, p plus p squared equal to 0. We already know from the summation before that this part is equal to 0. So we are left that mu of p squared is equal to 0. So we can generalize this, that mu, like we can go using the same method. So we'll always have that mu of p to the power of k is equal to 0 if k is greater than 1. And if k is equal to 1, then mu of p is equal to negative 1. And if k is equal to 0, then we have the base case here, mu is equal to 1. And since it's a multiplicative function, so we can compute so something like that. Here the powers will be all 1. So it's basically like that. So here, if there is any square of a prime that divides n, then basically this is equal to 0. Otherwise, we can just have this formula, because this we can distribute over each prime, and each prime makes a multiplication of negative 1. So the derivation of this formula, you can see it here. E1, E1, EK, EK. So this is the mu E1, E1 times the mu, all the numbers times the mu, like EK, EK. So any of these exponents is greater than 1, so we have the corresponding mu will be 0, so the whole product will equal to 0. So basically that's why we get this case here. So if there's any prime squared that divides n, then the mu is equal to 0. Otherwise, each of these will be equal to -1. And it's -1 multiplied k times. So that's why we get this case here. And also we find that if the number is equal to 1, then it has no prime factors, so this k will be 0, which will still get the right answer. So basically, we will say that mu of n is not equal to 0. N is square free. Square free means it's not divisible by the square of any number. So basically, this is how we can compute the mu. So from here, we can also notice here one of the properties that let's say the phi, which is the Euler's function, dot I, which is the function that returns always 1. This will be equal to the identity function. This we can prove that by trying, since this function is multiplicative, we just try to compute it for some power of p, where p is a prime. So this will be summation for all the exponents of pi power I, again times the I of p minus I, but this is equal to 1. So we want to put it here. So here this is equal to 1. We just exclude the first term, because as I said, we can't use the easy formula for the phi if here I is equal to 0. It's equal to this now. A phi e to the I so this is k e to the power I minus p power I minus 1. So as you can see, this is a telescoping summation. So basically we have here p1 minus p0 plus p2 minus p1 and so on until summation of p power k minus p of k minus 1. So here we end up having that this term cancels with this term, and this term cancels something here, and this here, and we are left with p to the power of k minus 1. We already have plus 1 here, so this is pk, which is the identity of pk. So basically here we just proved it for the power of p, where p is a prime, so we can generalize this for all the numbers. So here we have the proof. of this if we want. So there could be another way if we want to compute the phi. So basically, it's the identity function times the mu. So here, this is the Dirichlet problem. I will not be using this to compute it, but still, it's one of the bad ways. So here we can try to compute it fast. So here we start with, so still we'll try to compute the mu for all the numbers from 1 to n in the sieve-style way. So start first, all the mu's to be 0, and put 1, then yeah. So how, like, so the hard part here, so here we have to not make the optimization of checking. So we cannot here check if prime, because basically it's not related to the summation that we want to compute, or also this optimization of I squared. Here we need all the elements. So if we see it here, that we know that the summation, so for all the mu, so the summation is equal to this. So all the divisors, so this summation is equal to 0 if n is greater than 1. So basically you can get 5n is the sum of all the divisors of n, their mu value. So basically this is how we would construct our sieve. So we'll go for all the possible d, and then we update their multiples, kd, by the value of mu of d. And here this k has to be greater than 1, because we cannot update here. So because here the summation is not inclusive for this number. So if you want mu of n, we don't use mu of n somewhere. So because this might be in like the different case, in case we're counting the divisors or something, so as we did in the sieve lecture. So in case we want to like count without excluding this element, maybe this we can have here a different function. So here we could put the k is equal to 1. Basically you can go here, so this has to be like that, and then basically this is how we should compute it. Here we go from I is equal prime. Mu prime. Just do it in 330. Price now. As we can see here, so the 2 is prime, 3 is prime. The 4 here is divisible by 2 squares, so it's 0. 5 has 1 prime. The 6 has 2 primes, so the product is 1, and so on. The 8 and 9 are divisible by, so 2 squared and here 3 squared. As we can see here, so these are the values of the mu. So this is how we can compute the Mobius function. The other way is to by factorizing the number and use the formula which we had earlier. Here, not sure. Yes, so this will be the other way to compute the mu. So we factorize the number and check if it's square free, then return 0, then otherwise we count the number of primes. If it's odd, we return -1, if it's even, we return 1. So I just wanted to show the sieve idea because it might be a bit hard if you're not so comfortable with the sieve. So to make this loops here and how to update exactly, it might get tricky if you're not comfortable enough with the sieve. So that's why I wanted to show it here. Then we try to compute the phi also. The phi is actually a bit more tricky. Yeah. So for the Euler, we have this formula here. Yes, this formula for the phi. So here we can look at it as we have p to the power of k times some number m, which is not divisible by p. So basically this is phi of p power k times phi of m. which is p per k is minus 1 part m. So here we can have this part here. So from this equation, we can find the update rule. So how can we do that? So basically, if we here loop through all the prime divisors of p, sorry, the prime divisors of the number here, then we can update the phi by doing this operation here. So we multiply it by e to the power of k, and then we multiply by this number. Okay. Here, if we start with so the numbers will be initially the identity, so the number itself. Here we have to go through all the primes. Here we check a number is prime if the phi is equal to I minus 1. It means the I is prime. I hope this works. Equal p divided by Euler. Yeah. So as we can see, it computes the values of phi. I'll explain now the code. So here you can see that the phi of any prime number is indeed equal to this number minus 1, 5, and so on. It's the same for all the primes. So here, so basically what I did here, so I go, so the update of this equation would be something like this. So if we know that P is some prime divisor of this number, it's here I will assign this value to 5n minus phi n over P for all divisors of, for the prime divisors of P. Okay, I just have to excuse for 10 seconds. All right. So basically, this is the update rule, which would correspond to what we had here. So here it means, so I begin initially with the 5n is equal to n, and every prime divisor I see, I do this operation. So this basically means that 5n is equal to I would set it equal to the old 5n and this expression, which is basically 1 over. And this I will do for all the prime divisors of n, so I'll end up doing the operation what I want. So because this will eventually yield this equation that we had here, this one. So here I have to check, so if the number is 5i is still equal to I, it means that there was no any prime divisor that we had before. Because any prime divisors we meet, it will for sure increase, decrease the value of phi. Here it's still as the original, it means there was no any other prime number that made this change here. So basically, if this condition is true, then I is prime. So they can make this. But here still, again, we can't make the optimization of I squared, but here we have to make sure that the I is prime. So these are both show how like the variance of the same sieve idea, so how the sieve goes through its multiples. So it can be really useful to compute like other functions, like here the pi and the mu, and also the sum of divisors, number of divisors. So all of these can be computed easily using the sieve pattern. So the last part, or before the last part. So for this last two parts, I will be playing around with some multiplicative functions. So first, I have to introduce the Mobius inversion, which is a really strong formula. So here it says if we have some function g, if we have some function g, it is equal to the summation of b. So this divisors of summation over divisors of some other function f. Basically, this is f product I. So here we can find the f using the the following formula. We just multiply, like we make the dot operation here with I inverse, which is the mu. I inverse is the mu. So here we get like, so if we make dot product of mu on both sides, so we get that G is equal to F is equal to G dot mu. So this is called the inversion formula. So this is G. So this is what we have, and also it goes the other way around. So if this expression, if we have it, then we can just make a dot product with I both sides, so we get to this original expression. So this is the Mobius inversion theorem, and this can be generalized to include more functions and more patterns. I will show one of the generalizations of this inversion, which I got the idea from section 4.9, I think, in the concrete mathematics book. So it's the section talking about the mu and phi. So here, so the general form would be something like this. If f of x, and this x here is not, it doesn't have to be an integer. It can be actually like a vector or anything. I'll just assume it's a vector here. So we sum from k for 1 to infinity, g of x over k. This is equivalent to that g of x equal the summation k from 1 to infinity. Okay. So this is x over k. So both, so these two formulas correspond to each other. So this is the generalized form of Mobius inversion, and we have to make a condition that the function f and g are like convergent. So this summation of g of x over k, so from 1 to infinity, so this has to converge, and the same has to be for the f as well. So this is just a condition to guarantee that the equations are well defined and so on. So we start with proving the correspondence like in this direction, and then we do it in the other way. So we'll assume that this part here is true, this first part. Basically that f of x equal to summation g of x over k. So if we have this assumption, so we'll check this expression, and we'll try to go with it as much as we can. So this mu k f of x over k k from 1 to infinity. For this we can use the definition here that we have for the f. So, but we'll just rename this k to f. So because we already have a k. So mu of k times g x over. So here it's x over k. So this is the argument, and we have to divide it also by s. So sorry, by k. Because here it's f of x over k. So the argument is x over k, and here we have to divide it by this s. Call this an s. So we end up having this argument, which is put here, is x over k. So this we can redefine like this product x times s to be equal to d. Something wrong with the connection. Okay, then just to there we go. Okay, I think I have to create a new one. I can't, because I wasn't logged in, so I had to. I wasn't authorized to edit anymore. So infinity g of x over s. Here this expression again, write it. So k equal 1 here. Mu of k times f over k is equal to summation from k equal 1 infinity is equal 1 infinity mu of k times f of x over ks. So here I will proceed. So here I'll add a third summation actually to make things look more complex. K from 1 to infinity, s from 1 to infinity. And the third summation would be b from 1 to infinity, or let's call it n. So here we have mu of k x over n, and we put the condition that n is equal. So this third argument here would be equal to 1 only if this condition is true. So it will happen only when n is equal to ks, and then we substitute with the n here, ks, which is coming from here. Basically, this shared summation will always be like 0, except for one element when the n is equal to ks. So here we can get this expression, so these three summations are independent, so we can move them however we want. So we'll get this one out. So it will be n equal 1 to infinity. Then we have and here we can also get this f of xn, x over n. Because it doesn't depend on k or s anymore. So get it out. So and here we are left with. So here we can see that the s and k, they both have to divide n. Those k and s are integers, and n is also an integer. So instead of going from infinity, from all the numbers to infinity, you can just go through the divisors of n. And this is mu of k. And here the n has to be equal to k. So here, this part, we move this summation inside. We can make it like that. Summation of s divides n. Summation of k divides n. K and k. So this is the end part that we still have. So this is equal. We'll also move this summation outside. So k here s divides n. That that n is equal to ks. So basically, this will always be equal to 1, because this condition is true for exactly one value, where s is equal to n over k. And since we're going s for all the divisors, so n over k is one of the divisors of n. So this condition will be satisfied only one time, so we'll add 1 only when the s is equal to n over k, and otherwise we'll add 0. Basically, this is summation of k mu k, which, as we know from the definition, so this is equal to p of n. Because here this part is equal to like mu dot I, and mu dot I are the inverse of each other, so they're equal to the identity. Basically, if we get back to here, so this is equal to the summation for n 1. Oh, I'm sorry. Actually, here I should have put the g. I always do this mistake. This is g, and this is g. Here the summation from n equal 1 to infinity for g of x over n times e of n. So here all the e's will be equal to 0 unless n is equal to 1, so basically this is equal to 0. Which proves some part here which we have. So the part which we had earlier of the Mobius function. So this is the first part of the theorem. So it proves if we assume this condition, then we end up having this, that this expression here is equal to g of x. And then we can do also the other way around. So if we assume this expression here, already true, where g of x is equal summation of k equal 1 k f okay. So if we have this expression, then we check this we have here. If what do you want to prove? We want the summation of all g of x over k. Let's say, yeah, let's keep it k. Here we use the substitution of this. So basically we have k from 1 to infinity, and I'll rename this to s, so s from 1 to infinity, of s times f x over ks. So we'll use the same trick, so we'll introduce a third summation, d equal 1 to infinity, where mu of s f of x over n, x over n, and we'll put the condition n equal ks. So after we rearrange in the same manner that we did earlier, end up having so n from 1 to infinity, then we have f x over n, and we have here, so the k will go also through the divisors of n. So n equal ks, mu of k, which we know this is equal n from 1 to infinity for f x over n times e of n, which is equal f over x. So this jump here from this to this, we already proved it here in this slide, in this part. So this proved the other side of the equation. So I'll write it now again, just because we lost it in the last slide. F of x is equal to summation of all k equivalent that g of x equal to the summation of k 1 to infinity of k, f of x over k. So here, as I assumed that the k here doesn't have to be like a number, it can be any object that has scalar division. So it can be even a vector of numbers and so on. So this I would show an interesting example. And also here we can make a restriction that the summation can actually go up to some n, because we can assume some, like there's an fx would be equal to f of x is 0, if x is not equal to n, is otherwise. And so on. Something like that would restrict, so here the g would also be defined for something. So we end up having another g, which would also be g of x, or 0, x is not equal to n otherwise. So here we can still plug these formulas here. So we can replace the f smalls by the f capital and the g small by g capital. So still we can make the same argument here for a finite summation. Okay, so I'll then try to solve some problem. Is if we have a 2D grid with size n times m, something like that. So we'd like to count the lattice points that are, so we are standing at the origin, and we look on lattice points. For example, here, and look here, or here. And here we would say that we cannot look here because the line we look through already passes through another lattice point. So we can see a lattice points if the line, lattice point is a point where the coordinates are integers. So we can see xy if the line between xy and 0, 0 doesn't have any other lattice point. So another lattice point, let's say A and B. So this case will happen only if the numbers x, y are coprimes. Because if they are not coprimes, it means that there's like a part of the vector, this vector here, that is like still passing on some lattice point. For example, if we have xy equal to r times a and r times b, where r here is the GCD of xy, then it means that we're ready or passed by the point AB. We have this like r times. So here you can see that So here, example, this point is 1 and 2. And this is 2 and 4. So this has a GCD 2 because this vector from here to here is repeated 2 times. So it means there's another lattice point that we could use to get like on the same line. And also here from this point is 3 and 6. So the GCD between them is 3, which means that this vector is repeated like 3 times. So it's here and here and here. So, but here because we don't, the GCD is 1, it means that this vector that's not repeated before, it doesn't join, it doesn't go to a lattice points and still repeat itself somehow. These are the only cases that we get like these points that are visible. So this is not visible and so on. So we'd like to count the number of visible points in this grid. So basically we want to count the points x, y in this range. Such that the GCD of xy is equal to 1. So here I will define some function f. It takes like m, n, and k. So this is the summation for all. So it's the count of all pairs that has a GCD equal to k. So here we have this notation. So here if the GCD is equal to k, then here this expression means we will output 1, otherwise we return 0. So this means we are counting all the pairs that have a GCD equal to k. And these pairs are in this grid. So here we notice that so what we want to calculate is f, m, n, and 1. So this is the answer to the problem that we had earlier. The question is how to calculate this. So here we notice something that if we make this function f, we make a summation for k from 1. Let's say without loss of generality that m is greater than or equal n. Say that the m, so the sum of k from 1 to m, of this function so this is basically all the possible GCDs between x and y. So basically it's exactly the count of all the pairs like x, y. So this is n times 1. So to show this, just to make it more clear, so imagine we put here a third summation and we can force it inside here. So because these are not dependent on each other. And when we make a summation of this expression for all the k from 1 to m, basically one of these expressions has to be true, because here we are enumerating all the possible values of the GCD, which is the k from 1 to m. So exactly one of these expressions will be equal to 1. So it's as if we're just making a summation of 1 for all the pairs. So it's exactly the count of the pairs. So this is something we have to keep in mind. So the other observation here, we can see that like f, m, and k is actually f of n over k and n over k and 1. So here all the numbers that in the grid m times n that has a GCD k, it means this is equal to all the numbers in this smaller grid that has a GCD 1. Because if the GCD is k, then we can look in this grid. It means if something until this part here has a GCD of 3, like this part, so if the GCD is 3, it means there is some smaller vector that is repeated 3 times. So basically it's this vector. And this vector will be found in the dimensions when we divide each of these by 3. So when we divide each of these by 3, we have the 2, 1. Basically for have here, so all the numbers that will have a GCD of 3, so we have to divide this part by 3 and this part by 3, and then we count all the parts that have a GCD 1, and then so this will be like a smaller grid here. For example, let's say this is when we divide by 3, and let's say we found those 2 points. Then we multiply each of these vectors, we repeat it 3 times. So it's like that. And here we have something like that. So basically this is the intuition behind this formula. So why is this true? So let's call this f of n over k. Let's say here we will round down. So here it doesn't matter if we round down, if we floor. So this is a function f that we define it as to be equal to this expression. Combining these two, we have this so summation of k from 1 to n, or actually could say from k to infinity, make it look like the function that we want to get. And here's f capital. So f n over k and n over k. This is equal to m times n. So here, as we can see, this is our function, and we can say that this function basically is defined as g of m times n, where this function is basically just does that. So here we have a direct application on the theorem that we proved. So we have here the g of m and n is equal to this expression. You can say directly that so already we have a definition for g and we want to get the f. So we just do it this by inversion. So here f m and n equal to summation equal 1 to m mu of k times g of m over k and n over k. This will be the summation like that. Okay. And okay. Also, if we define the g in a different way, this could also be equal to something like that. I think both should yield the same result. We can try it out. So basically, this function capital F can be computed using this expression. So here we can find that instead of going through like all the pairs, so which has the complexity of time complexity of OMN, that's the old way. Using this method, we can just do it in O of M. And plus we have a pre-computation of M log n for to get the value of mu. And this can even, we can generalize this idea for a grid like r dimensions instead of 2. So this would be reduced from, let's say, n to the power of r will always be 2O of n log n. We have like a hypercube of n dimension. Like all the dimensions are of size n. And we have r dimensions. So to solve the same problem for instead of doing it in O of n to the power of r, we'll just do it in complexity of n log n. So this was one of the really interesting applications of on the Mobius inversion. Then I'll just solve a small problem related to multiplicative functions just to get an idea on how to do it. So let's say if we want to compute this f of n, where this is f of n if we want. Notice that this is not the Dirichlet product, so we cannot just generalize some stuff. So here we have first to prove that this f is multiplicative. So nm, we just want to compute this value, so we do it first to prove that the f is multiplicative. So here, say that b1 divides n and b2 divides n. So we have that n and m are coprimes, so we can get all the divisors of n and all the divisors of m and make the pairs. So this will be b2 by b1 b2 is equal. So if we make the same summation, b1 this we find that it's the summation. So we just separate the two summations that we have here. Phi of b1, and this is b2 mu of b2 times phi of b2. So all of this basically is equal to f of n times f of n. Okay, so here we proved that it's multiplicative function, so we can just try to compute it for some power of prime. Here you notice that this expression, this proof, I mean, is similar to how I proved the closure under so the closure of multiplicative functions, how they are still the product of two multiplicative functions is a multiplicative function, which I did the last lecture. Okay, so now we compute the f of p to the power e for some e. So this is the summation. All the divisors of p to the power of e will just go from I equals 0 until e for all these divisors. So mu to the power of e and pi to the power of I. So here we can see that this is enough to just do it until until this e equal 1, because all the other terms, if I is equal to 1, then mu of p to the power of I is equal to 0. So here we have f of 1. So this is equal to 1 because it's a multiplicative function. So which is basically the of 1 times phi of 1. And then we have f of p. This is mu of p times phi of 1 plus mu of 1 times phi of p. So this is negative 1, and this is p minus 1. So this is equal to p minus 2. And then here, if we have the summation of p to the power of 2, then it's the summation until here. Oh, sorry, here I mixed things up. I thought it's the Dirichlet product. This is 1, this is p. Actually, here we have the negative of this value, we have the positive. So here this expression is equal to 1, because this is 1 and this is 1. And here this is negative 1 times p minus 1. So actually, this is the answer, 2 minus p. And then when we put p squared, then this still it's 2 minus p, because it's the summation we have earlier plus 0, and so on. So this expression is equal to 2 minus p if p is greater than or equal 1, and otherwise it's equal to 1 if the e is equal to 0. So here we can find that we can compute f p to the power e1, so on, ek to the power ek is equal to 2 minus p1, 2 minus p2, and so on. 2 minus p. So I will just show a demonstration of those two parts in the code. So this function f and the solution to this grid issue they had here. So here, I'll say on grid. Oops. Here I'll just count them manually by going through all pairs. Yes, I have to check the GCD between x, y is equal to 1, and we just increase the result. So this is the brute force way. And the other way to compute this, down grid, where's the function? Here's the function that we want to compute. This can actually be the minimum instead of the maximum that we get. Here the result. So mu of k times n over k times n over k. And also, I will put this other formula and I'll make an assertion that they are both always the same. So here I'll make an assertion that they are both the same, as I expected it to be. We need algorithm and we need assertion. Here I calculate the Mobius, but I don't need the Euler for now. Let's keep the Euler as well. I removed the different statements we had earlier. So the count with brute force. So this would count integrate. Let's put the numbers to be primes. Antenna is not a prime, it's not a big deal. Here, because the mu is until 30, that's why I use these values. With plus same. Okay. Here I can put an assertion that they are both the same, and we can print one of them. The first one. Set the console nicer, and then we run. Here we have the result is actually not, I assumed here, seems to be not correct. So why is that? Neglected for now. Here, but here we are sure that the result here is the same. So the brute force method and the fast method are both getting the same result because this assertion passed. And the number we got as an output is this 388. Well, I'm not sure why is this. I have to check it out. Probably because it would be nice to see where the value is. Oh, I'm sorry. No, I don't think this is the actual. So this part here, there's something not correct about. So this should be true. That. This probably should be correct. Okay, I'll just leave this part for now. So this is basically not true. Here we have, so it all depends on how we define this G. Because I thought here if we put the G, if we put the definition of G of M and N to be this N, make it the product and then we round it down, then it means like if we have this, it still should make this formula valid here, this one. And then if we substitute with that here, it still get that m times n over k times k, this, and when we round it down should be equal. So this should have been true, but I'm not sure what I did wrong. No, yeah. So anyway, so I'll stop here. So in this lecture, I was just reviewing a lot of different properties about the multiplicative functions. So the Euler totient function, which is the phi, and the Mobius function, which is mu, and the Mobius inversion, and how to use it in solving seeing the lattice points, and also I solved some multiplicative functions in order to demonstrate how we can use the axioms and the theorems we derived in order to solve the solutions of some multiplicative functions. I know this probably was dense. I hope it was beneficial, and thanks for listening.